Welcome student to video lecture classes of digital circuit. I am going to discuss sequential logic. Let me define first the circuit whose output depends on both at present input as well as past output. So past output is stored in some memory elements called the present state of the memory element. Here is the block diagram of the sequential circuit. So memory element, which is consist of flip-flops, its output, which is called present state, is fed back to some combinational logic. Combinational logic with the input signal and the feedback signal from the output of the memory element generates some output signal. Hence, the output signal is the function of input function as well as the present state of the memory element. So this whole combines gives the sequential circuit. There are two types of sequential circuit. One is synchronous, another is asynchronous. In synchronous, signal affect the memory element only at discrete instant of time, and a periodic train of clock pulse from master generator is used to synchronize the memory elements. So here a master generated clock pulse will be controlling all the memory elements to synchronize their operation. And third point is, here it got interchanged, it do not manifest any instability. But in the case of asynchronous, it becomes unstable, and the behavior of a asynchronous sequential circuit depends upon the order in which its input signal changes and can be affected. At any instant of time. It means whenever there is input signal change, the output of the flip-flop can be changed in asynchronous. But in synchronous, input signal is changing, output signal will not be changing. Output signal will change only after the occurrence of clock pulse, and that clock pulse is generated by master clock generator. But in synchronous, at any time, based on the delay of the combinational logic, the output of the flip-flop can be changed, and the asynchronous circuit may become unstable sometime. That's why people are using synchronous circuit to remove the instability problem. Now, flip-flops, let me discuss. So memory elements used in the clock's sequential circuit are called the flip-flop. So let us discuss the basic flip-flop circuit first. Basic flip-flop can be constructed from two NAND gates or two NOR gates. The cross-coupled connection from the output of one gate to the input of the other gate constitutes a feedback path. For this reason, the circuit are classified as synchronous or asynchronous sequential circuit. So whatever basic flip-flop we are going to study, it is the asynchronous sequential circuit here. So let us discuss its working principle. So before going to detail of this working principle, let us first understand the truth table of the NOR gates. In the NOR gate, this is the truth table. So we see if any one of this input are 0, 1, any one input is 1, output is going to become 0. Output becomes 1 only when both the inputs are 0. So if to the NOR gate input is 1, any one input is 1, we can determine the output. So both the inputs are not needed to determine the output state if any one of the input is 1. So this we will use here. So suppose one of the input to the RS is 1 and another is 0. So we can see S is 1, so output will become 0 instantly. And if this is 0 and this is 0 is going here and R is also 0, so both 0 means output will become 1. So here Q is 1 and Q dash is 0. Once again, I am giving input to the SR is 1 and 0. So 1 to S and 0 to R. So when S is 1, here what is happening, this one, only one input can decide the output. And what will be the output then? In the case of NOR, output will be 0. And this 0 and this 0 both are coming here. So if both the inputs are 0, simultaneously the output will become 1. So Q is becoming 1 and Q dash is becoming 0 here. Now, if I am changing this 1 to 0, what will happen? Then, since this 1 is still here, this 1 is reaching here, it means this 1 will keep it in 0 state. And this 0, 0 will keep it in 1 state. So, nothing is going to change. So, it is 1, 0 again. Similarly, when now I am changing 0 to 1, this remains 0 and this becomes 1. This becomes 1. So what will happen? Again, this is 1. So output is, this is going to 0 instantly. And this 0 reaches here and this 0 is still there. So both 0 will bring this to 1. So 0, 1. So 0, 1. So remaining output you can see. But when both are 1, 1, both are 0, 0. This is invalid case because output of a flip-flop, both the output Q and Q dash cannot be the same. So this is invalid case. You cannot apply both the signal 1, 1 in RS basic flip-flop. Now, basic flip-flop with NAND gate. So here is again cross connection of NAND gate. So here again you can apply the same thing before going to study the truth table of this basic flip-flop. Let us understand this truth table of NAND gate. So you can see if any one of the input is 0, output is going to 1. And if both the inputs are 1, output is going to become 0. Remember again, if any one of the input is 0, output is going to 1. So in NAND gate, if only one input we know, and that is 0, the output can be determined. The output will become 1. No, both the inputs are required. So this is the property of NAND gate, and based on that property we can analyze this very easily. So at least one input should be 0. So let us start SR with 1, 0. So here we are giving 1, here we are giving 0. So since one input is 0, this is going to become 1. And since this is 1 and this is also 1, both input are 1, so this is going to become 0. So the output is 0 and 1. Now, next is 1, 1. So this is 1, this is 1, and previously, what was this? This was 0 and this was 1. So because we are applying sequentially, so previous state also has to be remembered. Now this 0 is reaching here. So one input is 0, so output is going to become 1, and this 1 is reaching here, so both 1, output is become 0. So no change is happening. So no change is happening here. So these two are the same state. Now if out of these two 1, 1, 1 is changed to 0. Suppose S is changed to 0. What will happen? Since one input is 0, this is going to become S is becoming 0. This is becoming 0. So output is becoming 1 instantly. And since this 1 is reaching here, both the input are become 1 now. So if both the input are 1, output is becoming 0. So in this case, 0, 1, output is 1, 0. So 0, 1, output is 1, 0. Similarly, you can see other outputs. So this is the very basic information about the NAND gate. If only one input of the NAND gate is 0, output becomes 1. And if both the inputs are 1, then output becomes 0. So remember all these things and you master on this operation of the basic flip-flop, SR flip-flop using NOR gate and NAND gate. Once you master this, you can do clocked SR flip-flop now. So what is clocked SR flip-flop? Suppose an AND gate is there, one input is A, another is clock. So what is the truth table? When clock is 0, output is 0, clock is 1, output is A. So A is transferred to the output when clock is 1. Otherwise output remains 0 when clock is 0. So based on this is the basic SR flip-flop and we are connecting AND gate to both the input and in combination with this clock pulse. So whenever clock pulse will be 1, this R will be reaching here and this S will be reaching here. So clock is controlling now and R and S. Whatever R, S be 1 or 0, that will reach here only when clock pulse is 1. If clock pulse is 0, both the input here will be 0. So again we can write a whole operation Q, S, R and Qt plus 1. What is the next state based on the previous state. So this is very much important to know here. When SR both are 0, 0, this I am deriving from the previous truth table. So if you remember this truth table, this previous truth table, this one, copy these things there, you can generate this truth table here. So if both the SR is 0 and Q present state is 0, nothing is going to change, output remains 0. So nothing magic is happening here, just if you match the previous one table to this, everything will follow. So if S is set input, R is reset. So if reset R is 1, it's going to reset the flip-flop. So flip-flop output is becoming 0, means reset. If S is 1 here, so it is set input, so it is going to set the flip-flop to 1. Again, if both is 1, 1, it is indeterminate case. If both is 0, no change condition. So no change condition means whatever previous state was there, it will carry out here. If R is 1, it is going to reset the output. If S is 1, it is going to set the output. If both 1, it is the indeterminate case because both 1 changes the Q and Q dash to 0, 0, which is not acceptable. So it's very much easy to understand, irrespective of the present state 0 or 1, if both the input S and R is 0, the output is not going to change. So what is output? 0. So if it is 0, this is 0. Here again both the input are 0, 0 SR, so output remains 1. So this is the present state, this is next state. So in this way you can understand this operation. This is the graphical symbol, SR input, Q and Q dash, and this can be, this whole circuit now can be minimized. So Qt plus 1 will become the function of QSR and that will be entered into the K-map. So here QSR is the input and Qt plus 1 is the output. So we have entered all the min terms. So there are two don't care conditions also. This indeterminate states are nothing but the don't care. So we are minimize. This 4 will give 1 S and this 1 and this 1 will give R dash Q. So Qt plus 1 is nothing but the S plus R dash Q, which is called the characteristic equation. So this is characteristic table, this is characteristic equation, this is a symbol, and this is the logic diagram. So these 4 things you have to remember, you have to know how to derive all these 4 things. Now D flip-flop, what is D flip-flop? It's one of the input S is given directly D and R or input of the SR flip-flop is given inverted D. So this is the NOT gate and it constitutes the D flip-flop. So its operation can be understood. So when we are giving S R, S I am giving 1, then R is becoming to automatically 0. When S is 0, R is becoming automatically 1. So out of this 8 combination, there will be only 4 combinations. Means when S is 0, R will be 1. Both 0 cannot be, and both 1 will not be there. So both input 0 0 cannot be there, because I am giving one input directly and one R output by inverted D. So you can filter out only the 4. So 0 0 0 1 1 0 1 1. Okay, when D is 0, means set is 0. So output is going to set. When D is 1, means reset is going, D is 1, means set is 1. So it's going to set. When again D is 0, D0 means reset is 1. So reset 1 means it's resetting. And when again it is D is 1 means set is 1. So it's 1. So you can see whatever D value is there, 0 1 0 1, Q is following the D, 0 1 0 1. So Qt plus 1 is nothing but equal to directly D. Qt plus 1 is equal to D. You can see the both 0 1 0 1 here 0 1 0 1. This is following. And you can see the same thing from the this schema. Enter this schema Qt for Qt plus 1. Input is Q and D. So these two minterm are entered, and you are finding that Qt plus 1 is equal to D is the characteristic equation for D flip flop. T flip flop now. Now JK flip flop. So JK flip flop is nothing but SR flip flop fed back. So this is the S, this is R. Here, remember when we are taking NOR, this becomes S, this becomes R. When we take here NAND, this becomes S, this becomes R. So in JK, because we are using NOR basic flip flop for SR flip flop, so this is S, this is R, and this is becoming J, this is K, and we are feeding back this Q dash to this and this Q to this, and we are putting this clock pulse also. Now by feeding back, we are again restricting only this 1 1 condition. When S R both were 1 1, then both output were becoming 0 0. No, that condition will not be here, because if one input is 1, the other output is feeding back from this side. So these both inputs are not simultaneously same thing previously. So the both the input here will be different. So if suppose one input is coming this 1 and this is 0 previously, so this 1 will come here, 0 will come here. What does this mean? Only one this 1 will be transferring here, other this 0 will be transferred here. So irrespective of this 2 1 1, here we are getting 1 0. So both 1 will never occur. That's why it simplifies the SR flip flop. It's an indeterminate case. So here, how to understand the working principle of JK flip-flop? It is similar to the SR flip-flop. So S is replaced by J and R is replaced by K. So whenever J is 1, output is going to become 1. So set, J is setting. And whenever K is 1, output is going to become 0. But when J, K both are 1, 1, we will see what is the previous state. So here, see J, K. Both 0, 0 means no change condition. So output is 0. Why output is 0? Because earlier it was 0. So this 0 is getting transferred to here. Again, you can see here both input 0, 0. So no change. So this one is transferring to here. Now what are the remaining case? If K is 1 means reset. So it is becoming 0 irrespective of the input. If J is 1, so J is 1 here and J is 1 here. In both cases, see the output is 1. Whenever J is 1, output is becoming 1. Whenever K is 0, output is becoming 0. But when both JK is 0, 0, the output is not going to change. So it follows the previous Q. Okay. Now, only the case we have to check both 1, 1. So both 1, 1 case is what? This one and this one. So when both 1, 1 and previous Q is 1, so you can check here Q is 1 and both is 1. So this one is becoming here. So both the input of the AND gate is 1. So this is 1. And since this is 0, 1 and this is 0, this 0 is reaching here. So this is becoming 0. So 1, 0. When 1, 0, so it's not going to change. This 1 will what? Set this into 1. I took wrong information here. So let us discuss this condition first. So present state is 1 and we are applying 1, 1 here. Present state is this one, 1, and we are applying both input 1, 1. So what's happening? Present state is 1. So this will be 0. This is reaching here and we are applying 1, 1. So this 1, 1 will generate this 1 and this 1 and this 0 will generate 0 here. So this 1 to the NOR gate will turn output to 0 and both 0 here will turn this to 0. So output is becoming 0. So in this case you see the output is becoming 0. Now take another case. This 1, 1. So present state is 0. So take this present state 0 and this is 1. So 0 is reaching here. So 0, 1 will make this one 0. And this 1 and 1, this will be 1. So what will happen? This one will turn the output to 0. This one will turn the output to 0. And because this 2, 0 is reaching here, this will become 1. So Q is becoming 1. So in this case, you can see the Q is becoming 1. So present state was 0. Both are applied to 1, 1. So it's 1. So what is this condition? You can see it is toggling. When both the inputs are 1, so present state is 0, it's toggle to 1, and when both the JK input is 1, present state 1 is changed to 0. So this both 1, 1 is called the toggle, both 0 is called the no change condition, 0, 1 is called the reset condition, 1, 0 is called the set condition. You can write all the here. So which is no change, this is no change, this is reset, this is 1, 0 means set, this is 1, 1 toggle. So toggle means it changes the condition of the present state. So next state will be the Q dash of, means whatever Q, it must be inverted. No, T flip-flop. T flip-flop is nothing but the when we give both the input of SR to the same value. It means both the input will be either 0 0 or 1 1. But it is not SR flip-flop. It is the, let me check once again. So there is some correction in the circuit. There is feedback, means JK flip-flop type of thing that must be corrected in all the PDF. I'll then do it and resend you the PDF. So this feedback is here. So it is like JK. In JK flip-flop, if both the input J and K are the same, so out of the 8 output input combination, there will be only 4 input condition. So both the JK will be either 0 0 or both will be 1 1. So when both J and K is 0 0, it will be no change condition. When both the input JK will be 1 1, it will be the toggle condition. So here we are seeing when T is 0, so there is no change. Means T is 0, so output will follow the input. T is 0, output will follow the input. Output means next state, input means present state. But when the T is 1, so this T is 1, T is 1, so it is toggle condition, means it will become, output will become 0 to 1 and output will become 1 to 0. So it's toggling. That's why it's called the toggle flip-flop. And you can find its truth table very easily. K-map. So K-map is nothing but the, so these two are 1 1. So Q dash T plus Q T dash. And the NOR operation of the T and Q is the output of the. So we have found all the 4 types, and it's a characteristic equation. In D flip-flop, it's a QT plus 1 is simply Q, and T flip-flop, it is the QT dash plus T dash Q means NOR operation. And in JK flip-flop, what was the JQ dash plus K dash Q? So you can remember this. In SR flip-flop, S plus R dash Q. So all the 4 characteristic equations must be remembered in order to handle the sequential circuit, which I am giving. I will give the example further. So now we can see the triggering of flip-flops. So switching state of flip-flops by changing the input signal momentarily is called the triggering. So when we change the input signal for some moment, then output state will switch, and that is called the triggering of flip-flop. So there may be level triggering and edge triggering. So asynchronous flip-flop such as the basic flip-flop as discussed for SR flip-flop, we use level triggering. So it is the 0 to 1. So till this time period, there will be no change in the output of the flip-flop. So whenever this one is high, clock is going to, the output of the flip-flop is not going to change. But in edge triggered, whenever this comes, this signal comes, positive clock or negative edge of the pulse comes, there will be change in the output of the flip-flop. So it is called the edge triggered flip-flop. There will be 2 types of edge triggering: positive edge triggering and negative edge triggering. This one is negative, this is the positive edge triggering. So master slave flip-flop. So in SR flip-flops, suppose clock pulse is like this, and in between S is changing 2, 3, 4 times. This one, this. What will happen? Output will keep on changing because this is the level triggering, and whenever this is high and input is changing, output is going to change. So in between, if S is changing, input S or R is changing 2-3 times, output will change 2-3 times. So even some small fluctuation in S will change the output. So what happens, to get rid of this problem, there is one master circuit SR flip-flop and there is slave. So first, whatever S is applied, suppose there is some fluctuation and then it get stabilizes. After fluctuating 2-3 times, it becomes 1, and final 1 will decide its output, whatever is its output 1. So there is one clock pulse which is controlling the master, and there is one negative of clock pulse is reaching to the slave. So whenever clock pulse is 1, this flip-flop is active and this is inactive because here 0 will reach. So once after fluctuating S, it stabilizes to some value of Y, and once clock pulse goes to 0 state, then only this stable output will become input of the slave. Now slave will change the output once the clock pulse is going to negative. So this output is not going to change all the time. So whatever it time takes to stabilize, it will affect here only. Once clock pulse is becoming negative, only that time the output of the slave is becoming, means changing. So this slave and this clock negative protects the frequent change in the output due to some fluctuations in S or R. So this is the master slave flip-flop. You might have understood. Once again I am repeating. If there is some fluctuation in S, so before becoming, suppose I want to set the value of S to 1, and before going to 1, it fluctuates 2-3 times, 0, 1, 0, 1, and then it is becoming 1. And this is my 1 clock pulse. So if there is no slave, output will change 2-3 times. It will become 1, again it will 0 till 1, 3 times. And if this output is connected to some another circuit, that circuit will be getting affected. Now, if I am connecting this slave with this not input of the clock, so whenever clock is 1, the output Y will fluctuate and become stable after some instant. At that time, this is inactive because clock pulse is 1. Only once the clock pulse is going to 0, then this becomes active, and whatever this stabilized value of the output will be the input of the slave, and hence the clock pulse will change the output Q. So this protects the any instability due to the fluctuation in S and R, and this is the master slave flip-flop. And this is the operation. You can see the clock pulse is 1, S is 1. So output wise is going to become 1 only at this, because here its level started, clock pulse level is started, so Y is changing. But Q will change only when the clock pulse is becoming 0. Only that time this key, final Q is changing. Y is changing in previously. Now, analysis of the clock sequential circuit. So, how to analyze the clock sequential circuit? So let me discuss this clocked analysis of clock sequential circuit into another video. This video is becoming longer. It will take longer time to upload on YouTube. So I'll make another video and I will refer there this video link. Thank you for watching.